So now third topic, regression analysis. Okay. Now earlier we had done this stuff, no? So given data xi comma yi, I had constructed curves or functions which will go through this point, right? That was interpolation. That was the first numerical algorithm I did. Okay. It could be, well, we did Lagrange interpolation or spline. These are two things. There, the function went through all the points. Okay, it was mandated that fxi or Pn actually. I had constructed polynomial of with nth order is Pni equal to xi, yi, Pni xi equal to yi. But this works when number of data points is small. We can do it with 5 points, 3 points, 10 points max. If you have 5,000 points, I cannot do this. It will be 5,000 order polynomial. Okay, and there are a lot of oscillations. Okay, so interpolation does not work for a lot of data points. In fact, it's meaningless to construct interpolation for when my data is scattered like here. It's obvious, no? I mean, anyone has a problem with that? We simply want to apply interpolation algorithm to construct a curve which goes through this 5,000 points. It's the same source, data source, which I'm not writing it here, but it's the same source. So what do we do with such data? Okay, so you need to, well, I mean, in your lab and all, I mean, everybody, engineering students, science students, you would have done this stuff, called linear regression. Okay, so this is the height of mean and weight of the mean. Okay, this is height of female and weight of females. Okay, generally we look at data. I mean, this data first plotted when they just plot them. Okay, scatter plot. Just put the data, and looks like persons who have more height have more weight. I mean, it's kind of natural that you have taller people will have more weight, more muscles. So it's you make a guess that W equal to AH plus B. Okay, and here, of course, all the 5,000 points, I want to make a guess that it's a linear function. And for this function, it's a good guess. Okay. How will you find A and B? Okay, so idea is you have a measure of error. Okay, so given hi, I make a guess that this is a fit. Okay, this fit of W. So I make a model and saying it is AHI minus B. Okay, given A and B, but real height is Wi for given hi. No, real weight, sorry, given hi, the real weight Whi. So it's error. So, well, I square it. Okay, so this is standard stuff. We want to minimize square error. Okay, so by minimization procedure, d by dA equal to 0, d by dB equal to 0. So these two variables are unknown. You just get, in fact, you just apply this partial derivative on that, you get two equations. And solve for these two equations, and that gives us A, this A, to be this. So this is average. So just take the data and compute WH average. So this is nothing but sum WIHI divided by number of points. Okay, that's how we compute average. Okay, any function, you just sum it up and divide by number of samples. So this average W, average H, divided by S squared average minus H average squared. Okay, that gives you E. This derivation is pretty straightforward. You can do it yourself. And B is nothing but, in fact, you can just do average here, like that. It comes from here. Okay, so this is A and B. For getting I mean, this is using regression. This whole thing is called linear regression, this procedure. Okay, so there's minimizing error. This is the constraint I'm putting. Of course, some people say, well, I can use a different function of E. One could use fourth power. Nobody stops you. Mod is not very easy function to use because derivatives are not so easy to get. But you can use different measures of E. Okay. In machine learning, first thing is regression. Okay. It could be complex regression, but this is one standard thing which is done in machine learning. Okay. So we can, okay, so these are A and B. Now A and B can have error, like sometimes, I get this A, but I have only 5,000 data points. Maybe this is not a real function, there's some error in this. So A and B are accurate only until some error bars. Okay, some error bars. Okay, it could be, well, I mean, it doesn't look good, but yeah, it could be some line here, something like that. So A and B always have error. So you need to give that error. Okay, A and B is not solid. That this is this by for certainty I can't say this is A. If I choose, let's say, 5,000 points, I choose 10,000 points, I'll get a different A. Okay, there will be a better model, but there's error always. So we can get the standard deviation in A and B. This is a measure of error. Okay, so if the standard deviation is a lot compared to the mean or A value, then you have to be careful. You should choose more points. So this is something always people compute. Okay, and how do we compute it? This is my model value. So Wi minus Wi hat square. So this is double called SWH, and given SWH, I can compute sigma. What did I do? Sigma B. This is sigma B, and this is sigma A. Okay, so this is error in A and this is error in B. Well, measure of error. This is a standard deviation. Okay. Now, this is a table. I mean, if you are interested, you may not be. So, this is men have average height from the data. Okay. This depends on geography, but the distribution is Gaussian all over the world. But the average will be differing. I mean, some countries are taller people and some have not so many tall people. So this is female always have less height at the moment. Okay. So this is average A. What did I do? Did I make a? No, this is A. Okay. So this is A and this is B. Okay. And error in A is 0.049. So you can see that it doesn't. It's quite small compared to 5.96. Okay. And B is error in B. See, standard deviation of B is 3.4 compared to this. Okay, so both sigma and sigma B are small, both for men and women. That means this is a good fit. If this sigma B was, let's say, 100, then it won't be a good fit. Okay, it's small compared to 224. I'm okay. Much small compared to 224. Okay. So, okay. Now, so this is how we do linear regression. Okay. I mean, you've done it in past. In every lab, you will be doing this linear regression. Normally, so I made this point before, human beings are good in fitting linear stuff. Okay, given the data you want to, linear is the best thing you can do. I mean, a linear line, I'm confident. But if the line is like that, I don't know. It's x squared, x cubed, x4, I don't know. Or like this, I don't know. So that's why we make log-log plot. If you have function like this, make a log-log plot. If this x power n, then this in log-log plot it becomes n log x. Okay, so in log-log plot it will be linear. So log y, right? Log y equal to n log x, and I can get n by getting the slope. So that's why power law or exponential is a good thing. If the function was exponential, I do a semi-log and see whether it is a straight line. So always look for a straight line. Okay, that's a basic thing. linear functions, linear differential equation. That's what we are good at. We can solve them analytically. But as soon as things become nonlinear, there's a problem. Okay, now that is linear fit, but we can also we can do nonlinear regression. Okay, so imagine that my function is this. Okay, now of course if the eta is the noise. Okay? It's from a uniform distribution. Okay? I just put a noise. So if only this much was there, then I could have, well, I can do with that as well, zero noise, but then the function is exact, okay? So I wanted some fluctuation. If this function is given there, then okay, this will be basically, it will be some function, there won't be any spread. But with eta, there will be some spread, okay? So there's some spread, but okay, this line is not exactly the same as this line, okay? Because of the noise. Okay? Now, if that is the case, then how do I find a fit to this function? Well, fit to the data points. Where are the data points? Okay, for many x I chosen, and I get a value of y, and this sampling, and I want to make a fit. So Python offers a very useful function called polyfit. So polyfit is going to make a fit, polynomial fit. Okay? Polyfit means polynomial fit of x and y with this number is the order of the polynomial. Okay, I want cubic polynomial. Okay, and residue. This residue is an error. Polynomial p will be a fit. So y fit minus y squared, sum over all data points. Okay, that's residue. Okay, now I can make a plot. Okay, so this is the plot which I showed you in the previous slide. This black line is a plot constructed using polyfit. And polyfit, that the coefficients are not exactly 0.2 and so on. Okay, so remember okay, so let's see. So x cube coefficient is p0, this one, which is small, 10 power minus 5. This is coefficient of x cube, like p0 here. Coefficient of x squared, this 0.302. Here it is 0.3. So it's close to the guess because my random number is kind of tiny random number. It has spread only up to 1. Okay, so 0.3021 and next one is the coefficient of x, which is here 0.2, and I get 0.195. Okay, 0.195, and next one is minus 1 here, but I get minus 0.649. Okay, so it's getting 0.469. Sorry, 649. So it is not close to minus 1. So this function is different because of the noise. Okay, but given any data, you can put a polyfit, no problem. If it is not linear, you can do quadratic, cubic, or x power 4, and this is called nonlinear regression. And how it is done, Python is doing it itself. Reasonably complex stuff. Machine learning is even more complicated. Okay, this is a fit. Okay? This is called nonlinear regression. Now, since I said if you want to do for this, I want to do Gaussian fit. Okay, I said I will show you how to do it. How do I do it? So my y equal to e to the power minus x minus mu whole squared by sigma squared and a. Okay, so you should do log first. Log of y equal to log of a minus log of this, which is x minus mu whole squared by sigma squared. Okay, now it is a quadratic function, no? Log of y is a quadratic function in x. Okay, so I do a polyfit of log y with x. So I'll get a coefficient of x squared should be 1. And coefficient of x will be what? 2 mu divided by sigma squared. And coefficient constant will be log a minus, well, plus or minus mu squared by sigma squared. Okay, so I can get all the 3 coefficients by doing polyfit. Okay, so that's how you can make a fit.